a great pleasure to introduce Professor Pramod Achar from LSU, who will speak on Arkhipov-Bezrukavnikov-Ginzburg.
Okay, great. Thanks. Yeah, so let me write down. I'll write down some overview picture, and then my rough plan is to spend maybe the first hour saying in detail something of what the components of the picture are, and the second hour. Saying sort of how to how to understand the functors. So I'm just going to write down a bunch of notation here without. I'll define all of it, but I will. I'll spend some time explaining what it is. So the first thing is called drep0 of G underline. The second thing is called db_triv of B underline. The third thing is called DG subscript co of N-tilda. And then above that, there's something that it's like this. Anyway, there's some other thing. And over here, there's something called parentheses I over K. And up here, there's mix parentheses I over K. And so far I've written a bunch of notation. I haven't said what any of it is. So the plan is explain all the components of this diagram. So the nodes and the arrows. Most of the arrows are equivalents. The theorems are going to say that they're equivalences of categories, except the vertical arrows are not equivalences. They're something else, which we'll discuss. And something I want to do is there's a K here. And K, I'm gonna discuss the characteristic zero case and the positive characteristic case simultaneously. Mainly because there are some things that I personally understand a bit better in the positive characteristic case, and so it's easier for me to explain. So the K equals C case is Arkhipov-Bezrukavnikov-Ginzburg, and the K of let's say FP bar case. All the components of the diagram exist, and the same theorems are true. And the contributors to this are myself and Laura Ryder, myself and Simon Risch, and Mautner. Various parts of this diagram and positive characteristic come from various of these authors. Okay. Okay, so I want to keep that diagram for the rest of the talk. So if you see me start erasing it, please yell at me to stop. Okay, so I think I'm just going to start at the beginning. So part one is let me explain the very first thing. This G underline. So part one is what is G underline, and I'm going to explain the positive characteristic case first, and then the let me explain the positive characteristic case first. Let me impose some assumptions. throughout, I'm going to use the letter P for the characteristic of K. So it might be 0 or it might be positive. If P is positive, then I'm going to require it to be not too small. I'm going to require it to be bigger than the Coxeter number for G. So an example is, I mean, this is not an enormous number. For if G equals GLN, then the Coxeter number is N. So that's what P bigger than the Coxeter number is. Okay, so G underline, yeah, to tell you what G underline is. So if P is positive, then G underline is a connected reductive group over the field. And then plain G without an underline is the Frobenius twist of G, of G underline, which is actually just, I mean, it's another copy of the same group. It's another copy of G underline, but they're going to play different roles, and it's going to be convenient to have different letters for these two copies of G because they do different things. And so because this is the Frobenius twist, these things come with a Frobenius map, which goes from G underline to G, and an example is, I mean, it's not just an example, it's kind of what, I mean, it's every example. If G equals GLN, then the Frobenius map is raise each entry to the pth power. Okay, so this is a group homomorphism because we're in characteristic P, and it comes with some other stuff. So so for G underline, I can choose a Borel subgroup and a maximal torus. So those are going to be called B underline and T underline, and I can also form their Frobenius twisted versions, which have no underlines. And when you look at the Frobenius map from T underline to T, so this is a map from a torus to itself, which is raising each element to the pth power. Well, what does it do on character lattices? So the character lattice of plain T without the underline, so an element of this is a map from T to the multiplicative group. If you can compose with that, then you get a character of T underline, which is P times some other character. So it identifies this with P times the character lattice of T underline. So of course, these are both free abelian groups of rank equal to whatever the dimension of the torus is. But this is something specific inside of here. Okay, so okay, so let me remind you that the irreducible representations of G underline are, of course, in bijection with dominant weights. Okay. And if I take a weight in here, I'm going to call the corresponding thing L of lambda. Okay. So So rep G underline means the category of finite dimensional algebraic representations, and it's certainly when the characteristic is positive and the group is anything other than a torus, this category is far from semi-simple. So there are lots of interesting indecomposable but not irreducible representations. There are lots of complicated X groups. It turns out that you can reduce a lot of questions about arbitrary finite dimensional representations to those in a certain subcategory, which is called rep 0 G underline. And this is called, I'm going to put the word extended in parentheses. I'm going to work with something called the extended principal block, and I'll explain what it is on the next board. The reason the word extended is in parentheses is that I'm going to write down a definition, which is sort of convenient for the framework of this theorem, and I might call it the principal block. And if you look up in Janssen's book or something like what he calls the principal block, it's something slightly smaller. And it's the differences the difference between the affine Borel group and the extended affine Borel group. So, there. Thanks. Okay, so here's the definition of rep 0 G underline. It's representations whose composition factors are of the form. So I'm going to write it down, or I'm going to write down a formula. So when I say composition factors, of course, everything, I mean, these are finite dimensional representations, so everything has a composition series. And I want to look at representations whose highest weight looks like this. W rho plus W P lambda minus rho, where lambda is any weight and little w is in the Borel group, and as usual, rho is the half sum of the positive roots. So one thing to be careful of here is that there's both a rho and a p, so I'll try to make them clear in my handwriting. If you take a random weight, like if you take lambda and w randomly, this may not be dominant, so then this has no meaning. So when I say composition factors of this form, composition factors where the highest weight, which is necessarily a dominant weight, can be written in this form. But you might, it turns out that this formula actually gives you a bijection. So this is what I'm going to write down a fact, which is basically a combinatorial fact. It's a, I mean, you can prove it just using sort of combinatorics of root systems. There's a bijection between the set of all weights and the set of dominant weights of the desired form. And here's how you get the bijection. If I take an arbitrary lambda in here, well, I send it to this formula, W rho plus W E lambda minus rho, where, and I have to tell you how to choose W, where W is the minimal element in the Borel group such that W lambda is dominant. Okay, so here's a bit of non-standard notation that that I find convenient. So basically, the simple objects in rep 0 G underline are labeled by dominant weights of this form, but I'd rather just label them by arbitrary weights via this bijection. And so I'm going to use the notation quotation marks lambda to mean this formula. For W is minimal such that W lambda is dominant. And so with this non-standard notation, the irreducible objects in rep 0 G underline are exactly the things of the form L quotation marks lambda, where lambda is anywhere. Okay. And let me make a comment about the easiest case of this formula. The easiest case is where lambda is already dominant, and then of course W is trivial. And then what this formula says is that if lambda is already dominant, quotation marks lambda is just P times lambda. And P times lambda means a character that you pull back through the Frobenius. Here's the note. If lambda is already dominant, then L of quotation marks lambda equals L of P times lambda. And this is the pullback along Frobenius. This is also called Frobenius twisted representation. So you can take the representation of honest highest weight lambda, and you think of it as a representation of G, not G underline. So I'm trying to, I'm trying to be careful about not forgetting the underlines. But anyway, if lambda is already dominant, then L quotation marks lambda is in the image of Frobenius twist. Okay. The reason I wanted to do all this is that the quantum group story. Yeah. So this was. I'm still on part one. What is G underline? And now I need to answer what is G underline in the case where P equals 0. And when I started preparing this, my assignment was to talk about ABG, and so ABG is about the quantum group story. And the thing is that so some people have a lot of prior experience with quantum groups at roots of unity, and some don't. And if you don't, it's a lot of it looks like it's a little bit unmotivated, and so somehow the thing you have to realize is that all these people in the 90s who are writing about quantum groups at roots of unity, they're all already experts on algebraic groups and positive characteristic, and they were writing for people who are like, oh yeah, I know what they're trying to do. They're trying to imitate this thing that we've known about since the 70s. But if you look at it as a second year graduate student, and there are all these formulas, and you're like, what are these formulas? And somehow they don't tell you, oh, this is the formula for the distribution algebra that Kostant discovered in 1972, but we put a Q in it. This kind of thing is. Oh man, I hope I don't say something false. Okay, so if P equals 0, so here's what I'm going to do. So choose an integer. Choose an integer L, greater than 0, odd, and not divisible by 3 if the root system you're interested in contains a factor of type G2. Okay. And then, so the reason for these restrictions are that I mean, I like at some point some computation messes up. Like, I mean, messes up if L is even, and the same type of computation also messes up if L is odd but divisible by 3 when you have something with type P2. But I don't. I mean, I never looked into the details. Like I can't know what computation it is. Okay, and then D underline. I'm going to use it to mean the Lustig quantum group at an Lth root of unity. And when I say Lustig quantum group, I mean this means so there are two types of quantum groups. I mean, when you want to specialize the quantum group at a root of unity, you need some algebra over the integers, and there are two kinds of quantum groups. There's the Lustig form and the Dick-and-Cheney-Katz form, and this is the sort of with divided powers. A lot of papers, like including ABG, like in the intro to the paper, they like write out the definition of a quantum group, and I think I don't want to do that because it's not really enlightening. Yeah, I'll say as opposed to the Dick-and-Cheney-Katz version. The key point is that this is a Hopf algebra over C, and it's a Hopf algebra over C, and of course the more standard notation would be something like would be something like U subscript Q of German G. But the whole theory is set up to have sort of as much in common with this characteristic P story as is reasonable. So one of the first remarkable features of this is that, yeah, so when you think of Frobenius, this is of course a characteristic P thing. If you take an algebraic group of the complex numbers, there's no such thing as Frobenius. But a quantum group at a root of unity does have something called a Frobenius, but its target is not a copy of itself. So over here, the target of Frobenius was another copy of the same thing. In the quantum group case, yeah, there's something called quantum Frobenius. And I guess this is the existence of this thing is due to Lustig. And it goes. I'm going to write it in sort of the usual notation for the moment, but then I'm going to switch to matching this underline notation. So it's a map of Hopf algebras from this quantum group to the usual universe enveloping algebra of the same root system. And of course, this is a complex Lie algebra. We're in this part of the talk, we're over the complex numbers. And informally, I want to write it as a map from G underline to G. So it's not literally a map from this. I mean, this is a Hopf algebra, not a literal group. This is a literal group, but you know, representations of this thing and representations of this thing are almost the same thing since we're in characteristic 0. And I'm not going to bother like the fact that they're not identical that doesn't make a difference. The main point is that you can take a representation of plane G, which is an algebraic group, regard it as a module for this universal enveloping algebra, and compose of this, and that's you can do Frobenius twist, and you get a representation of the quantum group that way. Okay. So you can informally write this. And then I want to keep going with this copying. So there's the quantum group G, there's a quantum Borel inside it, and there's a quantum torus. And those are all some certain Hopf algebras which I write with underlines. And I have also the honest algebraic groups G, B, and T. So okay, so the quantum Frobenius for the torus goes from T underline to T, and it identifies characters of the torus with L times the character lattice for the quantum torus. There's let me copy the next thing. So there's a bijection between irreducible representations of the quantum group and X plus. So I'm going to use the same notation. And inside rep underline G, I'm going to look at rep 0 underline G. So this is, again, the extended principal block. And now the composition factors are of the form L of W rho plus W L times lambda minus rho. So the only difference from here is that the letter P got changed to the letter L. And I want to again call this quotation marks lambda. And so irreducible objects in rep 0 G underline are in bijection with all weights, and the bijection is denoted by lambda goes to L of quotation marks lambda. Okay. Any questions so far?
Same thing where W is minimal such that
It's exactly the same set. Yeah. Yeah. So this, yeah, like when you prove this bijection, you don't actually need P to be prime. It's just purely combinatorial. I think you do need P. Oh, I probably should have said L was bigger than the Hassiter number. I think you need L to be bigger than the Hassiter number for this.
Also, do you assume like GSF is simply connected or adjoint type?
No, I think ABG probably does have some assumption like that, but you can I mean you can get rid of it. Like the statement, you can formulate the statements in a way that's valid for arbitrary reductive groups. Yes.
So in the quantum Frobenius picture, this other reductive group that comes in, this like metaplectic, it's some other reductive group. I think it's like the recipient of the quantum Frobenius.
There.
I learned this from like some completely different source, so maybe I'm just.
So there. Are there some? Is there something? Are there some like weird? There's like there's a kind of a traditional form of quantum Frobenius, but maybe there's some like something like related to exceptional isogenies of root systems that give you like maps to other groups.
Yeah, maybe so. So I thought there's this other. Sometimes people call it G sharp,
Uh-huh.
like this, and so I think it's also dualistic, but maybe it's different.
Okay, so the version that I'm using like literally goes to the Lie algebra with the same root system that you serve. Okay. Okay, so I'll keep that plan there. Okay, so that was I more or less finished explaining one term. Not every part is going to take as long as the first part. Part two is what is BB derived B underline, and this is easier to state. So we've got in both the quantum case and the positive characteristic case, we've got some kind of Frobenius map from B underline to B. And you can ask if you can make sense of its kernel. And when you're in positive characteristic, well, this is a map of algebraic groups, and you just take its kernel. The kernel is as a map of like on FP bar points, this map is a bijection. So looking at closed points doesn't tell you what the sort of scheme theoretic kernel is. So the kernel, the scheme theoretic kernel is an infinitesimal group scheme. So this means it's a group scheme whose coordinate ring has lots of nilpotents. In fact, it has only one closed point, and the usual notation for it in algebraic group world is B subscript 1, and the 1 stands for first Frobenius kernel. If you change that to a bigger number, that means you're taking a kernel of like a power of this map. In the P equals 0 case, you have to be a little bit more careful of what you mean by kernel, because it's not a map of groups. You can take something, I'm going to write it in quotation marks. It's something like the Hopf algebra kernel. And I'm not going to try to make this precise, but if you write down formulas for what these Hopf algebras, like if you write down formulas with generators and relations, anyway, it'll be this language will justify it. I want to use the same notation for both. So in the algebraic group case, it's usually called B subscript 1, or actually I guess underline B subscript 1, and I'll call it lowercase b underline. So this is the Frobenius kernel, and in this case, lowercase b underline is the small quantum Borel. Here's another basic thing that like it took me a long time to figure this out because like no one says it. Like, what the heck is a small quantum group? The small quantum group is the quantum version of Frobenius kernel. It's the kernel of Lustig's Frobenius map. But like lots of people, like if you read papers from the 90s, they're like, oh yeah, or the 2000s, they're like, oh yeah, here's the big quantum group and here's the small quantum group. And like, why is the small quantum group there? And the answer is kernel of Frobenius. Okay. So I haven't told you what D trig B is yet. So here's the definition. BB triv B underline is the full subcategory of, well, I could take the ordinary derived category of representations of capital B underline. And so whose objects M satisfy. So I need to tell you what full subcategory is. So here M is a chain complex of B underline representations. And what I want to require is that when I take the homology modules of this chain complex, so each of these is an underline B representation, and I could restrict it to the smaller group or Hopf algebra called lowercase b. Is trivial as a lowercase b module. Okay. So let me try to clarify. Let me try to say a bit more about what's in here. So if I just take the abelian category of B representation, of underlying B representations, and I intersect with BB triv B, that means I'm going to get underlying B representations that are trivial on the Frobenius kernel. And that's the same as representations of non-underlying B. And in particular, this thing, yeah, BB triv underline B is generated as a triangulated category by, well, by the things that generate this as an abelian like, I mean, the simple objects in here, by characters of B not underlined. Okay.
True that the entire derived category of B underline is is the same as the derived category of B without underline?
No, this is, yeah, so that's a good question. So this is very different from well, so the yeah, this is not this category. Is this what you were asking?
Yeah.
Yeah, this is not true. Okay. Okay. So, yeah, so I maybe a little bit later I'll mention an Ext calculation you can do to really see that these are far from being the same. Okay, so part 3 is what are G code N-tilda and G code G plus M N-tilda. Okay, so for this one, the treatment for positive characteristic and characteristic 0 is identical. So here's the definition. So N-tilda is the Springer resolution. So it's V cross B N with no underline. So in both characteristic 0 and characteristic P, I'm working with algebraic brackets here. And then I want to make the multiplicative group act on the vector. Yeah, so this N is the Lie algebra of the uniform radicals. And I want to make, and so this is a vector space, and I want to make G, the multiplicative group, act on it with weight minus 2. This action, so G acts on this thing. Another name for this is, I mean, not another name, but another description of it is it's the cotangent bundle of G mod B. G acts on this space by multiplication on the left. The multiplicative group acts on this factor, and these actions commute. So it makes sense to talk about G cross GM equivariant coherent sheaves on N-tilda. There's nothing particularly complicated there, but I want to point out that this whole space is set up for a kind of induction equivalence. So G cross G equivariant sheaves on this is identical to B cross GM equivariant sheaves on N. And this version is sometimes a little bit more convenient to work with because unlike N-tilda, N is an affine variety. And in fact, it's a vector space, so these are a coherent sheaf on it is a module over a polynomial ring. So the GM thing means graded modules. So this is the same as this. Excuse me. B equivariant finitely generated graded modules over the symmetric algebra on the dual. And because I made this act with weight -2, the grading on the symmetric algebra is in positive even degrees. So the degree of N dual is 2. Okay. When I look at the derived category of this, so an object in the derived category is a chain complex of these kinds of graded modules. So inside here, I can have a chain complex of graded modules. And I want to draw a little picture here. I imagine an internal grading that goes like this. So of course the algebra itself is only in even degrees, but you can have a module over it that has even components and odd components. So maybe there's a module, excuse me, a module that's supported in degrees -1 and up. And there's also a cohomological grading. And I'll put that going vertically. So like maybe in degree -2, you have a module that starts an internal grading degree -2 and anyway, well, some degrees. And now what I want to do is I want to do something slightly different. I've got a graded ring here. So instead of looking at 2 different gradings, I could identify the 2 gradings. And identifying the 2 gradings is the same as taking this graded ring, the symmetric algebra I have, and regarding it as a DG ring with trivial differential. Okay. Okay. So I can regard Sim n star as a DG ring with trivial differential. And then the definition of DG co N-tilda is the derived category of B equivariant finitely generated DG modules over sim n star. And there's a functor from the top category to the bottom category. And I'll show you on this double grading picture what it is. Basically, so I want to call that functor kappa, and kappa means you add up along these antidiagonals. So you take a chain complex and you just take the direct sum along each of those antidiagonals, and you get a DG module. Okay. Kappa equals sum along antidiagonals. Okay. So I'm not going to erase this, but I'm just going to label this arrow kappa. Okay. Okay. Part 4 is what are dB, I, K, and the mix. Okay, so GR is the affine Grassmannian for the dual group G check. Okay, so of course we had two groups on the first side. We had G underline and G, but they have the same root datum, and G check is something with the dual root datum. This might as well be over C. I mean, what the affine Grassmannian is over doesn't really matter. I mean, sometimes you might need it to be over a field of positive characteristic. Well, anyway, I'll say something about that in a moment. So this is like in loose terms, it's something like this. So I is the Iwari subgroup. So this is the it's the preimage of the Borel of the Borel B check inside G check under the map. We take G. If you take G with, I mean, the power series valued points of G, and you can map to the complex points of G by setting T equal to 0. Then inside here, you, oh, these should be checks, sorry. Yeah, inside here, there's checks. Okay. So I acts on the affine Grassmannian, the orbits are finite dimensional and their closures are also finite dimensional. The closure of each orbit is an ordinary projective variety. There's a bijection between I orbits and X. And this is the same X as earlier in the talk. So this is characters for T or co-characters for T check. Okay. And in fact, each I orbit is isomorphic to some affine space. So I'm going to define dB parentheses I over K to be the category of complexes of sheaves of K vector spaces with the following properties. One is that the support should be compact. So the support should be a finite union of I orbit closures. It's supported on finitely many I orbits. I orbit closures. And it should be constructible with respect to the stratification by I orbits. And just a warning, the reason that the letter I in parentheses is in parentheses here is that if you omit the parentheses, it looks like the I equivariant derived category, and that's something different. So everything that's I equivariant is constructible with respect to the I orbits, but not vice versa. So this is not the I equivariant derived category. So the I equivariant derived category does also occur in other places in this story, but not right here. Okay. Okay, and then D mix parentheses I over K. This is some kind of enriched version with an extra internal grading. And so hi. So how do you edit? So you haven't missed anything so far. I began by drawing this diagram. I've spent like 50 minutes defining the things in the diagram. So how do you get it? In characteristic 0, I think you can use mixed L-adic sheaves. I shouldn't call it L because the L has to be a prime number, but it doesn't have anything to do with the L, which is my root of unity for the quantum group. And I can't use P, and the only the only possible letters for the adic numbers are P and L.
Maybe it's Q.
Q? Mixed Q adic sheaves? Like lowercase q for a prime?
I probably would have used Q for the root of unity.
Okay, yeah. Mixed, how about I'll just say prime-adic sheaves. So in the ABG paper, what they use is mixed L-adic sheaves. You can also use mixed Hodge modules. And in positive characteristic, it's a slightly different construction. There's a construction you can do based on parity sheaves, and this was developed in about a little more than 10 years ago in a series of papers by myself and Simon Rich. And there's one arrow here, which I'll also call kappa, and kappa is forget the mixed structure. Well, I haven't been really explicit about what these things are, but with both mixed L-adic sheaves and mixed Hodge modules, what it means to forget to an unenriched kind of sheaf theory is sort of built into the notion. It turns out that in this parity sheaf setting, it's not built in, and in fact, the existence of this existence of a functor that forgets the mixed structure is highly non-trivial, and it's a theorem of Bezrukavnikov and Rich that it exists.
Which paper?
Well, it's a consequence of this series of new paper. Yeah, I mean these papers that I don't know the titles of any of them, but I think there's
some cell in the affine algebra, some particular cell.
Yeah, so the first paper in the series was about like passing to a quotient related to a regular unipotent element. So I think maybe in the second paper in that series, it's not the main theorem, but somehow like a consequence of something they proved the existence of this. Okay, so do you normally take a break?
Yeah.
So maybe now's a good time for a break. That would be nostalgia. Okay. Okay, so let's okay, so when I was preparing these notes, I wrote the notes and I said at the beginning that I'll spend an hour saying what the things in the diagram are, but I thought I thought I was overestimating, and I was like, well, we can go. Anyway, we're behind where I thought we would be. Well, anyway, let's just keep going. We'll get through as much as we can. So, oops, this is part 5. Of some Ext-calculations. Okay. So I'm going to write down some theorems that are internal to various of these categories, and they motivate the idea that the categories should be related to each other. So the first one is in the leftmost category. So if I take Ext in the category of G underline, so I haven't defined G underline before, but it's what you think it is. It's the Frobenius kernel for the small quantum. and I want to take the trivial representation. I'm going to take X of the trivial representation with itself. So in the quantum group case, K is C. And the theorem says that this is actually the coordinate ring of the nilpotent cone. And not just are these isomorphic, so this is a, well, this is a graded ring. This is a ring and I make it graded by letting GM act on N by weight -2. So this is another small detail that the first time I read a lot of these papers, 20 years ago or something, every single paper say, oh, let GM act with weight -2. And I'd be like, why? Why not -1? And the answer is that in this theorem, the left-hand side comes with a grading because it's an Ext algebra, and you want to match it. That's the reason it's -2. Okay, but also G acts on both of these. So this is not underline G, the algebraic group G, and this is a G equivariant isomorphism. And this theorem, when in positive characteristic, this is from the mid-80s, and there are 4 names that go with it, and so this was proved in a paper of Anderson Janssen and also Friedlander partial, and I never remember. One of them came slightly first, and one of them has slightly weaker hypotheses, and I never remember which.
I think the proof is still the same.
Yeah.
Which paper?
And then the quantum group version is due to Victor and Sean Kumar. And so this was like 1985 or so, and this is I think 1993 or so. Okay. Here's number 2. So I'm going to tell you several X calculations. So this one kind of lives in the first category. I'm going to tell you a related fact that lives in the second category. And that's if I take X over the Frobenius kernel of the Borel or the small quantum Borel. And this is almost the same theorem. So again, this is an isomorphism of graded algebras, and it's an isomorphism of B equivariant graded algebras. And well, that theorem and this theorem are closely related. I think they're. I think you can find them in the same papers. So there's the same references as part 1, and and in rough terms, you get the X calculation in part 1 from part 2 by applying some kind of induction functor, by applying induction from B to G. So on the right-hand side, it's literally true that if you induce this representation from the Borel to G, you get this, and on the left-hand side, you have to understand why applying an induction functor makes sense. Okay. Okay, so next for part 3, let curly R be the coordinate ring of G as a G representation by left multiplication. So this is the regular representation of G. Okay. So here's a fact. So I'm going to take Ext in the third category on the bottom row there in DG co N-tilda. And what I want to take Ext of is I'm going to take Ext of the structure sheaf of N-tilda with the structure sheaf of N-tilda tensor with R. And this is like tensor over C with R. And you could complain that this kind of doesn't make sense. I mean, definitely one way in which I'm being a bit sloppy is that R is not finite dimensional. So if I tensor by an infinite dimensional vector space, I'm not getting a coherent sheaf anymore. So I'm finding that subscript. Let's not worry about that. The other thing that's happening here is that R is a ring. It's not just a representation, it's also a ring. And so when I write this thing down, well, of course, if I didn't have this R here, it would have, I mean, it's an Ext algebra, so it has some ring structure anyway. There's a slightly more involved ring structure on this that involves the multiplication on this as well. So let me just say, the ring structure is slightly more complicated than you expect. Well, not complicated. Let's say slightly more. And I'll tell you what ring it is. It's the coordinate ring of the nilpotent code. And this is G equivariant again. And in this instance, we get the G action because G acts on this.
Somehow just come down to the fact that like
Yes. Yeah. Yeah, this one is kind of easier than yeah, it's I don't know if it's easier. I mean, it's different. Like I mean, it involves the fact that the derived push forward of the structure sheet from N-tilda to N is doesn't have higher derived functors. Yeah, the vanishing of higher cohomology. Yeah. Okay. And then the last one is about the affine Grassmannian. And the Ext in the derived category of the affine Grassmannian. So I want to take the skyscraper sheaf, so we'll call it IC0. Skyscraper sheaf. At the base point. And then the other thing I want to take is the image of R under geometric syntactic. So this is slightly sloppy in the same way as this. R is not finite dimensional, it's some union of finite dimensional things. So this syntactic of R is not a perverse sheaf, it's an end perverse sheaf. But that's okay. It turns out that this this Ext thing is finite dimensional in each degree. It's a graded ring, and by now you can guess what the ring is. It's the coordinate ring of the nilpotent cone. And for k equals c, this is theorem of Victor. M5 for sense. And then for positive characteristic, it follows from work of Jiwei Yun and Xinwenju. Something like that. Okay, so here's where we are. I've told you what every category is here, and I've written down an Ext calculation in each of the bottom four that kind of gives you the same answer. And so roughly, the objects I wrote down in those Ext calculations, they're kind of not so far from determining the whole category. And so what's left to do is kind of to actually construct the functor. Well, a lot is left to do. To construct the functors and prove that they are equivalences. Finding the functors. Okay. Let me label these numbers. So this is going to be 1. Number 1 is going to be the easiest. Number 2 is going to be the second easiest. I'll put 2 prime here, and 3 is going to be the hardest. Okay. So the functor is the derived induction functor from underline Borel to underline G. And if you just think about induction in general, of course, it would take you from representations of underline B to representations of underline G. So by the way, so if you want to know basic properties of this functor, in the algebraic group case, you read about it in Janssen's book, and you learn key things like Kemp's vanishing theorem and all this kind of stuff. The fact that the analogous theorems are true in the quantum case, I think is mostly in a paper of Anderson, Polo, Wen, which somewhat contains the foundations of representation theory and of quantum groups and the root of unity. And then the key fact is that inside here, if you look at dB triv B, it's sort of a kind of an elementary fact that so this is generated by characters of plane B, which are characters of underline B that are divisible by P, and those things get sent to the principal one. I've told you nothing about how to prove this is an equivalence, but this is the easiest functor to define.
Define the principal block this way as like the image of this functor somehow? Or
Sure, yeah. Yeah, like you could define it as the full triangulated subcategory generated by the image of this thing. And if you say it that way, then I mean this is a direct sum n in here. You don't. If you define it that way, maybe you don't see right away that it's a direct sum n, but
somehow it's more comprehensive.
yeah. Okay. For number 2. Okay, here's what I want to do. So for a dominant weight lambda, I want to consider R gamma of N tilde, and I want to take the structure sheaf on N tilde twisted by lambda. And it turns out that for every dominant weight, these derived global sections are actually, they have no higher cohomology. And you can take the direct sum of these. I'm going to call it A. So I'm going to take the direct sum over all dominant weights. And this forms a graded ring, a kind of multi-graded ring. So of course the 0th part is a ring by itself. It's the coordinate ring. But if you take a section of O lambda and a section of O mu, you can multiply them and you get a section of O lambda plus mu. So this is an X graded ring. So it's graded by the character lattice. And you can recover the variety N-tilda from A by some kind of proj construction. So by kind of multi-proj. And this is the key observation that we're going to use to construct the functor in number 2. So okay, so given curly F in D mix I over K, I'm going to let F hat of curly F be the following. So I'm going to take a direct sum over all dominant weights of the following. So I'm going to take Ext. I want to basically generalize this thing. And instead of taking just the skyscraper, I'm going to do something more general. I'm not going to take other ICs. I'm going to take something called standard sheaves. So I'm going to write something called J lambda freak of the constant sheaf with some appropriate shift. I'll just put a question mark there. And here J lambda is the inclusion of an orbit for the Uhori into the affine Grassmannian. And I want to take that X out of that. Oh, sorry, this should be negative lambda. It's the Uhori orbit labeled by an anti-dominant weight. And then I want to take S, and then the star is convolution of the sort they have in geometric syntactics. So this is B of power series convolution. Oh, and this should be syntactic of okay, so this construction gives you an X-graded A module. So you have a module, you have a graded module over this graded ring. There's some kind of multi-proj you can do to get back the variety from this ring. And going along with that, there's some construction that takes graded modules over this graded ring, and and then it produces a coherent sheaf. So via multi-proj, you get a functor from D mix I over K to B co plus GM and O. Okay, so that's the top arrow. 2' is very similar. You don't actually need any new ideas. You just have to pay attention to a few technical details that are a little bit different. But Okay. Okay, so error number 3 is the hardest to define. So here's, I'm gonna start writing a construction. We'll see what we need to do. So the first thing we're gonna do is choose an injective resolution of the trivial representation. So this is some chain complex of injective modules, but this is as a lowercase b underline module. So small quantum Borel or Frobenius kernel of the Borel. And so when you have this explicit injective resolution, you can form the DG algebra. I'm going to write it as Hom underline. I'm not sure. Yeah, I think the underline is just to tell you that it's not. I'm not just taking a vector space. I'm taking some kind of chain complex Hom, and it's a DG algebra. Wait, do you have a question or? Okay, it's okay. Yeah, so I haven't been very precise here. So the easiest way to say this is that so I'll tell you what happens in the positive characteristic case and the characteristic 0 case. I mean, the positive characteristic argument is also valid there, so you could literally repeat it. But I think that the what's actually in the ADG paper is a tiny bit different. But an object here is a chain complex of parity sheaves. And so what I need to do is actually just define this for a single parity sheaf. And then my output is a single coherent sheaf via this multi-proj. And then when I plug in a chain complex of parity sheaves, I get a chain complex of coherent. Was that your question? Okay. So for in characteristic 0, you can literally do the same thing if you take a mixed dialectic sheaf and you write it as there's a way to make sense of writing it as a chain complex of pure objects, and then that's how you present it. Okay, so you get a DG algebra here, and then oops.
That's the bad shock anyway.
Yeah. Oh, that was the bad shot. Oh, sorry. I was supposed to be using the.
There's a piece right there.
Okay. 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 So by abstract nonsense, let me call this algebra. Let me give it a name. I'm going to call it C. By abstract nonsense, you can show that dB triv of not the thing we actually want, but lowercase b instead. This is equivalent to some category of like a derived category of DG modules over C. And I mean, you have to put in some like finitely generated condition or something to make it match the D here. But this is not the thing we want. And so here's, so we need to upgrade it. And here are what the needed upgrades are. Okay, so one is that we need to make B act on C. It doesn't have an action of that group to begin with. Then we need to upgrade this to something like DB triv B underline equivalent to the category of B equivariant DG C modules. So currently the goal we're working on is defining this functor number 3, and I haven't said anything about that yet. I'm just stuck on giving you alternative descriptions of the category in the second spot there. But then the last upgrade is to show that there exists a B equivariant quasi-isomorphism of DG rings from the symmetric algebra on N star to C. And once you do that, well, if there's such a quasi-isomorphism, I mean, the other category there, that DG co N tilde, that's literally defined in terms of of these things. So when you combine these, you get dB triv underline B is equivalent to eco and tilde. So this is a bit of a different flavor from the others. By the time you finish constructing the functor, you've also shown it's an equivalence. Like constructing the functor and showing that the two categories are equivalent are not different problems. But these upgrades take a bit of work. For the upgrades, so in characteristic 0, this is in ABG, and in positive characteristic, this is to myself and Simon Rich. And I want to just say a little bit about like how you actually do it. So in our paper, the choice of injective resolution is different. And the reason is that in ABG, the construction of this B equivariant quasi-isomorphism. So this is called the formality theorem, by the way. The property is called formality. So the argument in ABG uses some kind of deformation theory and Hochschild homology or Hochschild cohomology, and we weren't able to figure out, like we couldn't figure out how to adapt these results to positive characteristic. So the thing is that in ABG, the injective resolution they pick is kind of just, you can start with anything, just take an injective resolution, like of course it exists. And then the hard work is in this machinery, and this is in a separate paper by BG, and it provides a machinery to carry out these upgrades. So in positive characteristic, we couldn't figure out how to adapt this. But what we did figure out is that if you spend more work at the beginning writing down, like you put a lot more work into choosing an injective resolution carefully that you can manage, then you can just write down this map by hand, and you don't need deformation machinery. And at some point I think the so you can write down the quasi-isomorphism by hand. So where the hard work is kind of different in these two arguments. And when we were writing this paper, I'm pretty sure we decided that resolution we wrote down also makes sense in the quantum setting, and it would provide a new proof of the quantum version as well. And we had written, like, at some point we started writing the paper to like do the positive characteristic case and reprove the quantum case simultaneously. And then the paper just got to be so long, and then at some point someone decided to just delete all the quantum stuff. So like somewhere there's a LaTeX file which has like a bunch of calculations with an injective resolution that's valid in the quantum setting, and I don't remember if we got far enough to really convince ourselves that our proof also works in the quantum setting or not. But so anyway, if you want to find out how, I can send you a LaTeX file that's.
So maybe may I make a comment on this? Because for me, personally, this is the hardest part of IBG is to prove this formality. And in fact, I think historically is if you go to we had to write a separate short paper with Roman on this. And I mean, the whole idea about this argument was essentially Greenfeld's sentence. But the point is that this sentence is now at the heart of many other things. I mean, Greenfeld phrased this as point times a point, which is now called inertia stack or maybe Hochschild homology. And this is kind of at the heart of this formality statement, if you look at the proof. And I think if we didn't do it, but I mean, if we trace it all the way through Satake, I mean, to the affine Grassmannian part, it should correspond to basically the same derived Satake business, which is again, basically derived Satake's point. Not like inertia. Have a product of a point times a point over some like adjoint quotient G by mod G, something like that. And it's exactly the same thing that happens on the other side on the quantum formality for quantum groups. Although, and they should match, but we didn't do this, but so it's really some important point here.
Yeah, I think, yeah, this is, this is, I think, yeah, the formality statement is the hardest part.
So when you say formality, it's like, do you mean it's you can prove it at the level of cohomology, and the hard part is showing?
No, it's a very strange statement. It's still very mysterious. And basically, how do you ensure that? I mean, you have to do something B equivariantly. B is not semi-simple, not reductive. So there's no, you really need to show that somehow prove that you can split things with respect to a non-reductive group. And it's an ingenious trick by Roman. You use Steinberg representation. So it's really some extremely non-trivial thing. And I have no idea. It's this homological idea of Greenfeld, but plus Steinberg. But it's a combination of a lot of, basically. So why is it formal? It's still kind of.
Yeah, so let me mention that the Steinberg, yeah, so the thing you mentioned about the Steinberg representation. So this is some kind of special representation of the quantum group at a root of unity has this, and reductive groups and positive characteristic also have this. And it's something that it's a representation that has a lot of special properties. It's it's irreducible, but also tilting. It's projective and injective when you regard it as a module for the small quantum group or the Frobenius kernel. And yeah, so as Victor said, it appears in the formality stuff in ABG, and it also appears like it also appears somewhere in our paper. But I in fact I never understood if it was like if it was for the same reason or not.
Well, Steinberg also appears when you try to prove Frobenius splitting, for instance, for
Yeah.
B.
Yeah.
Probably it's also related. I don't know.
Yeah. Okay. Yeah. So maybe yeah. So with they use this thing called the Steinberg representation. Okay, so here's the last part of the talk. So part 7. Proving the equivalences. Okay. So so I've got various labeled arrows here. So for number 3, by the time we finish constructing the functor, we're done already. The formality theorem is proved in the process of constructing that functor. Let's talk about number 2. So so we've got a functor from one triangulated category to another. So the first thing we're going to show is that its image generates the target triangulated category. So step 1 is that this functor, let me label it F. So this is F. This is the derived induction functor. And this doesn't have a name. This is just called formality. Okay, so step 1 is that F of something called a Wakimoto sheaf. So I didn't define this, but I guess last week there was a talk that had Wakimoto sheaves in it. So step 1 is to show that F sends a Wakimoto sheaf to a twist of the structure sheaf. Okay, and these things generate the target category. So so step 2. Well, if you have a functor of triangulated categories whose image generates it, then all you have to do is prove that it's fully faithful. Then it's an equivalence. So to prove, so you need to prove that it's fully faithful. And it's enough to check on some suitable set of generating objects. Now the problem is that if I take 2 objects, in order to, when I say suitable, suitable should mean that I know how to compute Ext between them on the affine Grassmannian, and I also know how to compute Ext between them after applying F and ending up in coherent sheaves. And the thing is that, like, the easiest perverse sheaves you might think of, like standard and co-standard sheaves, at this stage in the process, we don't know what they are on N-tilde. In fact, they turn out to be related to something called the exotic T structure. But at this stage, we don't know that. So we need objects that are manageable on the coherent side, and it's a kind of funny set. So here's a lemma. E mix I over K is generated by. So I'm going to take Wakimoto sheaves where the label is not less than 0 in the partial order on weights. And then that's not enough. That doesn't generate the category. But if I take the unit of that with Wakimoto sheaves convolved with these are co-standard, or maybe I'll just write it this way. Geometric satake applied to a dual Weil module. of highest weight mu. So here, lambda and mu are both dominant. This is a kind of funny looking set. But it turns out to be, so this is the set that they used in ABG, and it's, I don't know how they thought of it, but it's a set that like, it's not obvious that it generates, it's not hard, it's a little exercise, but it's not the first that you'd think of, but it does generate the category, and it's manageable in that you can compute Ext on both sides. And then in positive characteristic, like you use the exact same set, and then you can do the exact same calculation. Okay, so that's number 2. And then what's left is number 1. So the proof for this in ABG is different. It's structured differently. It's a similar kind of thing. Like, you already know that the image of the functor generates the target category, so you need to show that it's fully faithful. And the argument for this in ABG, I didn't prepare, and now I won't. Since Victor is here, you should ask him what the argument is. But I'll tell you the argument that's in my paper with Simon, which is a little bit. It's slightly different, but it uses the rest of the diagram. Okay, so the plan is expand the whole diagram like this. So if S is a simple reflection, then I've got dB rep 0 G, but then I can so this is called the principal block, and there's a non-principal block attached to the simple reflection S. And there are functors back and forth called translation functors. And over here, I've got dB triv B underline. And there's an analogous thing here. It's not triv anymore. It has the label Stein. And the thing it involves is a parabolic labeled by S. And there are functors back and forth here. The next step, well, I won't write down the bottom row. I'll just write down the top row here. So this is T star G mod B, and then there are functors back and forth to coherent sheaves on T star G mod P, PS. And the last step is here's a D mix I K, and the analog here is well, I'm going to put IW, and the IW stands for Iwahori-Whittaker. So there's some Whittaker condition involving S, and there are averaging functors that go back and forth here. So, so in our paper, we're considering not just this diagram, but these parabolic versions at every step of the process. So we've already got this whole diagram. And the advantage of having this whole diagram is that at this point, we already know this is an equivalence. This is an equivalence. This is, well, this is a degrading functor combined with composed with an equivalence. So this is degrading. And the advantage of having this whole diagram is that now when you look at the whole composition, you can say something really concrete about where standard and co-standard sheaves go to. A standard sheaf goes to a Weil module and a costandard sheaf goes to a dual Weil module. And once you know that, then the whole composition is a degrading functor, and that means that this little part is an equivalence. So okay, it's 559.
Any questions for?
May I make a comment or maybe a question? I don't know, but I want to go to the board. There's something I realized only about a year ago, very confusing about all papers, including ABG and everything else about the affine Grassmannian. And so I want to, well, I hope I kind of understood now what's going on, but not quite. But so let me try to explain it. Now, first of all, there was this object Ext from IC not R or Satakov R. So first of all, this has a kind of simple, it looks like something strange, but in fact, this is completely general thing. So first, we have some monoidal category, and basically, which is in our case, the Sataki or whatever. So, and in this category, we have the monoidal unit object. And then essentially what we want to do is we want to compute Holmes or R Holmes or whatever from this object to itself. So that would mean here that I put IC naught here. But the reason we put this is what is called de-equivalentization. And basically, since we're working in this equivariant derived category, what we really want to compute the Holmes with non-equivalent, it's the usual Holmes. But in the equivariant category, I mean, it's basically you take first usual Holmes and then take only those which are equivariant. Now, so it kills a lot. We don't want to kill it. Now, the way not to kill it is to say that in order to have a Holm between two representations of G, so I have two representations of some G, and I want to take Holm between two V prime, but now I want to really take Holm as vector spaces. Now, what you do is just tensor one of them by the regular representation, which is R, and then the compute equivariant. So this is called de-equivalentization. So that's the reason for this. So this is not my question. Now the issue is that let's forget about this for now. Let's just look whatever this is. Now, but what is the ring structure on this? And this becomes very confusing. There are two. Namely, an obvious one, and this is what I thought we used and everyone else used until last year, is that whenever you have just the Yoneda composition, and it doesn't matter whether it's one or not one, you put it from X to X, and then you compose it with you can compose them, get another one. But there's another one, which is essential, where it is essential that this is a monoidal unit. Namely, well, you can imagine that since one tensor one, with respect to this monoidal structure is still one, you can count, plug in, so basically you can, now I will get lost. So you're using that one tensor one is one and plug it in, and then you can also create an algebra structure out of that. Now, which one do we use? This was very confusing. And for example, the reason I start looking at it that in the papers on completely different thing, on this Kuhn branches on BFM papers, it's the same story, and also in BF and in all other papers. If you carefully look, it's completely not clear which of the ring structures do they use. Not clear at all. But the wonderful fact is that, which I learned, and then I checked right now on ABG, kind of it's implicitly used. This issue is well known in algebraic topology. This is called Ekman-Hilton principle, which says that if you have a monoid with two operations, then under some natural assumptions, they're actually equal. The same happens here. They're actually equal, but it's not clear to me. But for instance, with rotation of the loop, they're not equal at all. Just period. They're not equal. And you do not get the same thing at all. And that's a big problem. I mean, this is well known that that's why this rotation of the loop Satake is not an E3 or whatever fancy name is it. The real issue is here that it's not, well, I mean, one has also to upgrade it to a format, replace R home by X or whatever, prove some formality. But basically the source of the problem is here that there are two multiplications and it's not clear which one do we actually use in the proof. Now, hopefully, I mean, fortunately, without rotation of the loop, they turn out to be equal, but it's not, it's an abstract kind of thing. It's not easy to trace it kind of explicitly. Yeah, so I just wanted to emphasize whatever paper you read on this business, when you have this R, it's a ring. That's true, but sometimes you use ionada composition, which has nothing to do with this ring. And without rotation of the loop, it turns out to give the same structure, which is not clear at all. Really very confusing. So I still don't know. The same thing happens to, that's why working about some, these quantum groups, whatever, called algebras. So again, there are two kinds of operations you can do, either ionada or this kind of monoidal thing coming from algebra. And again, at some point, it's important that they actually produce the same thing on the X. Which is this abstract.
Somehow conceptually they play slightly different roles, like in derived Satake, for example.
Absolutely.
Right. So like if you prove that sort of they're isomorphic for this kind of ionada composition, that's saying the two categories are abstractly isomorphic, and then saying that the version that comes from the monoidal structure, they're isomorphic as such, is saying that they're equivalent as monoidal categories.
No, I think it's even more to this. I mean, I think it's in Rink and Ginzburg think that actually with rotation of the loop, there are two ways of quantize, and they're not equivalent. Right? There's one which is
with loop rotation.
Yeah, then there's one basic, and this is the same problem. But there's one by causal duality. I mean, this is what is called BV quantization on one side, which is I think more related to this monoidal thing. And there is another way where you kind of just naively try to do it. And this is what I mean. At the Euclidean level, they're equivalent, and so that's why BF work. But at the higher level, I think they're not equivalent. Just period.